Okay, welcome back. Happy Monday. Today is May the 1st. Project number 8 is officially due. Throw it in the folder which you do not have. Again, I'll take it late is that yours? That might not be yours. I'll take it late if you don't have it just yet, but throw it in the folder if you have it. So today we're going to do Finding and Applying Taylor Series. It is our very last day of new material before the test. Wednesday coming up is our review day for the test. I have no specific agenda. I'll just come in and talk generally about the test for about 5 minutes, and then you guys will hopefully work on the practice problems packet or the textbook homework problems or something like that in preparation for the test, which is coming up on Friday. Just looking ahead beyond this week, we've got hardly anything left. This week is a full week, so is next week. Next week, we've got 1, 2, 3 days of new material. That's Monday, Wednesday, Friday next week. That's the end of the new material. The last day of the semester is Monday. That's 2 weeks from today. That's our review day for the final exam, which is scheduled for 2 weeks from Wednesday. It's going to be right here in this room, 8 to 10, although I'll give you some more time. Okay, so also coming up, we got the tests we talked about. Project number 9, I will hand you Monday, a week from today, and you'll hand it back to me on the last day of the semester. I'm also going to hand you Project 10 kind of in rapid succession here. Normally, I don't have 2 projects at the same time in this class, so a couple of things are going on. Project 9 is brand new for me in this class. I've taught this class a few times here, and I've never given this project before, but some students in previous Calc 2 classes had asked for a project on differential equations, which is our last topic, so they asked and you get. Project number 10, if you remember, the last project of last semester was just an opportunity to reflect on the semester. So it is a project and it counts the same as all the other projects, but the median grade on that project is 100 because all I need you to do is, like take your time and answer the questions thoughtfully and you'll get 100, okay? So hopefully not stressful, but an opportunity to think about the semester and also give me some feedback. Quiz number 6. In theory, is due on Monday, the last day of the semester. That wasn't the original schedule, but we've had several snow days that pushed some things down. In looking at this calendar over the weekend, I realized that if you hand me this project on the quiz on the last day of the semester, you will not have an opportunity to get it back, and the whole point of the quiz is to get feedback before each of the tests. So I've decided to make this quiz I'm taking it off of the table. I'm not going to delete it from here, but I will hand you the quiz on the day that I thought that I was going to hand it to you. And if you give it to me on the last day of the semester and then come find me later on that day, or maybe the next day is a Tuesday, I will give it back to you with feedback. I won't grade it. I won't count the grade any place, but if you do want that feedback, you can have it. But quiz 6 is now canceled. Okay? Any questions on the very little that's left of this semester? Okay, so I think we're here on page 60. Today we explore Taylor series further. The process we've seen for getting Taylor series is cumbersome. Today we'll explore some alternatives. So remember the process for Taylor series. Stay right there on page 60, but our process involved doing this kind of thing. Like I give you a function, x e to the x, and I give you an a value, and then you calculate maybe half a dozen derivatives, and then you plug in the value, in this case is 0, into those derivatives. And then we have to divide by what kinds of numbers? The factorials, all right? You divide by the right factorial, and then you multiply by x minus a to the right power, right? And then you've got like half a dozen terms here, and then you just add them all up, and that's our Taylor series. And there's nothing super hard about that, but it is a process. Sometimes you can get to the final answer, that is the Taylor series, without going through that entire process. And that's a little bit of what we're after today. So here's some alternatives. Number 1, you could substitute into an existing Taylor series sometimes. So for example, if we want to find the Taylor series and the interval of convergence for ln of 1 minus 2x, normally you would just start that process. Find 6 derivatives of that function, plug in well, it doesn't say here, but x equals the 0, I think is our a value. You plug in, you divide by your factorials, you tack on x to the right power, okay? But we're going to do this one much quicker. Here is a fact. We proved this, I think it was last class, that the Taylor series for ln of 1 plus x is this thing, okay? We did this together in the demo. So the question is, how can I turn this into this? What do I need to change or maybe replace x with to turn the 1 plus x into the 1 minus 2x? Yeah, negative 2x will do it. You're going to change the x to a negative 2x. Agree? Well, if I'm changing the x on the left-hand side to negative 2x, then I should change all the x's on the right-hand side to negative 2x, and that is all that we need to do. So ln of 1 plus, and then I'm just going to write the shell here. I don't know, we'll see if this works out. I hope that it looks readable. I'm just trying to copy all of this stuff in the Taylor series that's written there, but instead of x, I'm just putting blank parentheses. I think I've got it. Okay. And as you said, we're going to change all the x's to negative 2x. So that's just what's going in the blanks. 1 plus negative 2x, that's the goal. And then all of these blanks, maybe I should have put one more parentheses here. All these blanks become negative 2x. And there's hardly anything else to do. We're basically done. I'll write one more step here. I don't quite have enough space. Trying to squeeze it in down here. Negative 2x minus, what do you get when you square this thing in here? We got 4x squared, right? 4x squared, and that's divided by 2. You could reduce, I'm not going to. What do you get when you cube this thing in here? Negative 8x cubed. Negative 8x cubed, still divide by 3. Last one. 16 x to the 4. Okay, looks like they're all negative. I just got increasing powers of 2 on the top and the same pattern on the denominator as we did before. That's it. That's your Taylor series. And if you had done the regular process, which means like half a dozen derivatives and then plug in and divide by the factorials and simplify, you'd have gotten exactly that. But goodness, this is a whole lot easier, isn't it? So sometimes you can build the new series based on one that you've already created. Also asks here for us to find the interval of convergence. So this should have been written down here, but the interval of convergence for this original one was all the x's between, and I think it was it -1 to, somebody help me out here. 1, it went up to 1, I remember that. And then on the other side, I think it's -1. Anybody? Yeah. Okay, so that was the original interval of convergence, and we proved that using the ratio test. Well, you could use the ratio test on this blue one, but again, there is a shortcut. And the shortcut is to say, hey, all we did was replace x with negative 2x. So in this interval of convergence, all we're going to do is replace x with negative 2x. So here we go. So for this guy, interval of convergence, the x becomes negative 2x. But the -1 and the 1 and the inequality symbols all get copied. So just one change. And what do we do to get x by itself? Divide everything by -2, right? So we get a positive 1/2 over there, x in the middle, negative 1/2 over here. First inequality becomes greater because whenever you divide by a negative, and the next inequality becomes greater than or equal, right? Just flip it around. That's it. That's your new interval of convergence. Again, a whole heck of a lot easier than the alternative, which is the ratio test, right? Full-fledged ratio test. And eventually you get down to that. Any questions on that? Okay, next one. So sometimes you can make a brand new Taylor series by multiplying or dividing. So this one says find the Taylor series for x squared ln of 1 minus 2x. Now ln of 1 minus 2x is the Taylor series we just created, right? And so what do you think we're going to do to this Taylor series to create the new Taylor series? We're going to multiply everything by x squared. That's it. Let's multiply everything, all that blue stuff, by x squared. So the first term becomes negative 2x to the third minus. I'm not reducing any fractions here. That's the new power of x. Remember, everything is getting multiplied by this x squared right here. So what's this one? X to the 4 minus, I got an 8, I got a 3, x to the 5th minus 16 over 4, x to the 6. That's it. And again, I want to point out how much better this is than the alternative. We're done. The alternative is to start from scratch, meaning you take this as your original function and you calculate like half a dozen derivatives, which means a product rule a bunch of times. And as soon as you do the first product rule and the derivative of this, you're going to have a fraction, right? 1 over 1 minus 2x, which means quotient rules inside of those product rules. And you just do it 6 times, and it's massive and it's messy, and it will get you to this answer. So again, it's nice to be able to use previously built Taylor series to get new ones, to get related new ones. Any questions on that? Okay, let's take a look at number 3. It says we now derive, really we create is what we mean there. We now create a formula for e to the I theta, which leads to the absolute most awesomest equations in all of mathematics. So at the end of this, we're going to write down what is my favorite equation in the universe. I'm sure you have your own, right? Like we could debate this, but we're going to build mine right here. And it's interesting, maybe 2 weeks ago, I read an article about a study that was done where they took something like 200 like mathematicians and they put them into like MRIs, like those machines where like you get like brain scans and stuff. I think that's the right word. Is that the right word? Like a brain scan thing. And they like would flash on the screen like a certain equation. And then they would look at what parts of the brain lit up in these mathematicians' minds. And then they would hide that, like they would just let it sit there for like a few seconds, and then they would get rid of that, and then they would show another equation. And these would be like all famous equations, right? And it was just the same list of equations that they showed to all these mathematicians. And based on like what like parts of the brain light up, you can tell like how enthusiastic or excited somebody is about what they are seeing. And the equation that we're going to come up with right here was the like most brain dopamine inducing equation for these mathematicians as a whole. So just get ready, all right? Okay, but put your pencils down. You don't need to write any of this stuff down. I do want to say that this equation right here is going to relate 5 of the most fundamental numbers in all of mathematics. It is going to relate 0 and 1 and pi and e and I. One equation is going to relate those 5 numbers. Those 5 numbers, like I said, are fundamental. 0 is the magic thing where if you add it to anything, it doesn't change the thing, right? 7 plus 0 is 0. 0 is the only number with that property. 1 is the magic thing where you can multiply and it doesn't change, right? 7 times 1 is 7. 1 is the only number with that property. Pi is related to circles and about a billion other things. E is related to like compound interest and about a billion other things. And I is the number that generates the expansion of the real numbers into the set of complex numbers, right? 5 fundamental numbers are going to be related by one elegant equation. Here we go. I've also written some stuff on the sideboard. Again, you can stay here if you want. I will show you that we had a reference sheet. I don't think we've even looked at this reference sheet. Where is it? This one here. So it's like might be labeled page 1. Here are 5 famous Taylor series. The bottom one is the one that we just used, ln of 1 plus x, right? E to the x equals 1 plus x squared over 2 plus x cubed over 3 factorial We proved this one. We created that one either last class or the one before. I've written that in red over on the top. Just confirm that what I've written over on the sideboard in red at the top is the same as this one, which we saw. Yep, it's good. The next two we also need, cosine and sine. Now, we didn't prove these. I don't think even they were in the activity. Like, they might have been referenced in the activity, but I don't think you created either of these. But you just do it from scratch, take half a dozen derivatives, plug in, do the factorials, and these are the things you get. So again, just make sure I faithfully copied sine and cosine on the sideboard there. Feeling good? Okay, so I put them on the sideboard because I don't want to keep flipping back and forth up here on the smartboard. So I think we have all of the pieces that we need. So here we go. We are going to begin by creating a formula for e to the I theta. And I've got a formula for e to anything, right? Taking a look up on the board, I have e to the x. What am I changing x to? I theta, that's it. So I'm just going to write that top formula again. You don't need to copy any of this stuff down. I theta squared over 2 factorial, I theta cubed over 3 factorial, I theta to the 4 over 4 factorial. Maybe one more for good measure. Okay, everybody agree? All the x's just become I theta. Okay, now we're just going to rewrite this guy by squaring everything inside. So this is going to become an I squared theta squared. Yeah? Next one. I cubed theta cubed. Everybody see what we're doing? Okay, good there. All right, next up, we're going to clean up some of these i's here. This equals 1 plus I theta plus, get rid of that. What is I squared? I squared is negative 1. I squared is negative 1, which means this just becomes a minus theta squared over 2 factorial. You with me? Right, I squared is negative 1. I cubed, let me over here on the side. I squared is negative 1. I cubed just means multiply the previous thing by another I. So what is it? Negative I. And then I to the 4th says multiply the previous thing by another I, and you get negative I times, so it's a negative I times another I. And that's negative I squared, but I squared is negative 1. So this is really 1. Okay, those are the only 4 that we'll need there. And it just repeats this pattern here. Okay, so I think we're moving on. Okay, so we're up to I cubed. What is I cubed? It's negative I. So this becomes negative I theta cubed over 3 factorial. Good. Next one is I to the 4th. What is that? Plus 1. So that's just a plus theta to the 4. Next one is I to the 5th. What is that? That's really, I to the 5th is the same as I, just loops back around. So this I to the 5th just becomes plain old I. So far, so good. And we can see the pattern here. It goes 1, I, minus 1, minus I. 1, I, minus 1, minus I. That's the loop. Okay, next up. Half of these terms have I in them and half of them do not. We're going to shuffle the terms around. First, the ones with no I. 1, what's the next term with no I? Minus theta squared over 2 factorial, right? What's the next term with no I? Plus theta 4 over 4 factorial. I didn't write it, but looking at this pattern, what's going to be the next term with no I? Minus theta to the 6 over 6 factorial, right? Okay, I'm going to put this in parentheses, dot, 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 that stuff. That's just the ones with no I. Plus, every other term has I, and I'm going to factor the I out of all of the other terms right now. So the first term with an I is this I theta. When I factor I out, you just have theta. The next term with an I is minus I theta cubed over 3 factorial. That I is in the front and becomes plus theta cubed or minus theta cubed. Minus theta cubed over 3 factorial. Next one with an I is here. When you pull it out, what do you get? Plus theta to the 5th over 5 factorial. It's not written, but looking at the pattern in here, what's the next term? Minus theta to the 7 over 7 factorial plus dot, dot, dot. Everybody with me? Okay. And after all of that rewriting, take a look at this thing in the parentheses. and take a look over at the sideboard. This is the same as one of those, but instead of x, it's theta. What is this? This is cosine of theta, yes? Look at the cosine. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial is this, just theta. So that means that this whole thing equals cosine of not x, but theta, right? Plus I times, let's look in the second parentheses, and look over on the sideboard. What is it? That is sine, yes? Sine of theta. I'll put a little dot for times there. So there we go. So when all is said and done, we have just shown that e to the I theta is cosine of theta plus I sine of theta. I think we've seen the name Euler a few different times. This is called Euler's formula. It's actually one of many things called Euler's formula. This guy did a lot of stuff. Okay, but so this is cool on its own right because it gives meaning to taking E and raising it to an imaginary power. Taking E and raising it to an imaginary power. You just think of that power, whatever's next to the I, you just think of it as an angle, even if it's not an angle. You just treat it like an angle, and E to an imaginary thing times an angle is really just cosine of that angle plus I times sine of that angle. And these are just numbers over here. Right, and so it just becomes like an a plus bi, just a regular old complex number. Okay, and so that means you can pick any theta you want and throw it in here. And so the theta that I want to pick is pi. And so that means that e to the I pi equals what? Cosine pi plus I sine pi, right? Just all the thetas become pi's. And what is cosine of pi? That's -1, and plus I times sine of pi. That is 0. So this whole thing is just -1, right? So what that means is that e to the I pi is -1. And that equation is lovely, and you could just stop right there if you want, but if you really want to get all 5 of our fundamental constants into the same equation, you'll solve for 0, which is a thing you've done many times in your life. So what do you get when you move this guy? Equals 0. There we go. One simple, elegant equation with 5 of the most important numbers in the universe. It's got 0, it's got 1, it's got pi, it's got e, it even has I in there for good measure. Like the dopamine centers in your brain are just exploding right now, right? It's crazy. It's crazy, like why should that be true? Why should that be true? Like if you just, like if you try to do something simpler than this, right? Like, like even simpler than this, e to the pi I would be e to the pi, right? Second e to the second pi. It's nothing. It's stupid. It's meaningless, right? E to the pi, which is far simpler than e to the pi I, there's nothing good going on inside of there. But somehow when you tack an I onto it, magic happens. And it's just -1. I actually think your calculator knows this. I don't know how it knows it, but I think it does. There's a little I down here right above the decimal point. What am I hoping it gives me? -1. Hey. E to the pi, ridiculous number, but e to the pi I, -1. Used to go to Rubik's Cube competitions, and there was one. Well, there were a bunch of competitions where I helped out. I was part of the organizing team or whatever. And at some of these bigger ones, they happen not just over the course of one Saturday, but all weekend, like a nationals competition. And to make sure that all the competitors know who's working, and if they have questions or whatever, you can we'd all wear these matching shirts, whatever. And so at some of the competitions, they would put your name, so it would say Winokur at the top here, and at this one thing, it had not just your name, but it said, hey, what number do you want to put? And people would just put a jersey number, a sports, and so I said put e to the 2 pi I. I was joking around. I said put that as my number. So real quick, what is that equal to? So that would be not cosine pi, but cosine of 2 pi. What is cosine of 2 pi? That's 1. What is sine of 2 pi? 0. So what is e to the 2 pi? This is 1, right? And so, like, I wanted my jersey to be number 1, but I just sort of, who just puts 1? You got to put something more interesting. So I put e to the 2 pi I, and I didn't think it could happen, but they worked with their shirt person and they made it happen. So it was no problem. And the funny thing is that, you know, like you'd imagine a Rubik's Cube competition is like a nerd convention, right? And so like if I walk around almost anywhere in the world with the shirt that says e to the 2 pi I just get funny looks. But at this one, I get like awkward high fives and, oh, that's awesome. And so great. Yeah. All right. I think that, what's that? Okay, so activity starts on the next page. Let's see how far we can get.